So again, welcome to another season and year of Saturday Morning Physics. It's really great to have everybody here, and we're really, really grateful for your support of Saturday Morning Physics by attending lectures and, of course, the financial support that many of you have offered. So I'm pleased today to introduce our speaker, who is Professor Kai Sun of the Physics Department here at the University of Michigan. Professor Sun studied and got his undergraduate degree at Peking University in China, and then his PhD in physics from the University of Illinois in Urbana-Champaign in 2009. And then he came to Michigan, to the University of Michigan, to join our physics department in 2012, and has been here ever since. Professor Sun is an expert in theoretical condensed matter physics, and he has described himself, I love this, as a pencil and paper, or maybe paper and pencil theorist. So he has expertise in the behavior of systems with many bodies, in particular topology and the geometrical structure and geometrical concepts in quantum mechanics. So we're really excited to have you here today and to hear your lecture entitled From Nobel Prize Research to the Breakthrough Technologies Transforming Our Lives. Professor Sun.
Okay, good morning, everyone. Can you all hear me? Okay, great. So it's my great pleasure to be here today. And before I start today's talk, let me briefly introduce myself and a little bit about my research. So we know that in modern physics, the research can be largely split into three main branches. That's high-energy physics, low-energy physics, and astrophysics. So high-energy physics focus on physics phenomena at a very small length scale, typically either nuclear length scale or subnuclear length scale. And our astro and cosmology colleagues study the other end of length scales, extremely large length scales, the size of the universe, the size of the galaxy, and the size of star or planets. So I studied low-energy physics. It's fit right in the middle. And the physics length scale involved in our study typically range from size of an atom to the size of a human and up to the size of a planet. Okay. And beneath these three main branches, there are many subcategories, subfields of physics. And this is a list of subfields of from the American Institute of Physics. And the numbers here describes the number of PhD students graduated from each of the subfields. According to these statistics, we can plot a pie chart. So roughly speaking, about half of the graduate students graduated from a PhD graduate program studies low-energy physics. About another quarter studies high-energy physics. Slightly less than a quarter study astrophysics and cosmology, and the rest either study topics described as others or computational physics. And my research area is this low-energy physics. Okay, and let's go back. Here. Okay, let's go back to these statistics. Here I circled the sub-areas belongs to low-energy physics, and myself mainly study condensed matter physics, which is the top one atom in this list. And I also have significant research effort in AMO physics, atom, molecule, and optics, and in soft matter. And in addition, I also have some research efforts in these areas marked as small arrows. Okay, so that's most about myself. So let's skip these slides. Okay, so as you have known, I'm a theorist. And if you Google theoretical physicist, and the Google image will give you pages or pages about pictures Google believes to be theoretical physicist. Okay, if we look at these pictures, and actually there are pages or pages of these pictures. If we look at these pictures, there is something in common for most of these photos. That is the blackboard. If you look at these photos, you will find that almost every single one of them has a blackboard as a background. I find the most ridiculous one is this one. It is actually a picture of a robotic theoretical physicist. And instead of doing the calculation using his computer brain and print out the result, he decided to go to a blackboard and write down everything, use a piece of chalk on blackboard. Okay? So although I do love Blackboard, and especially for lectures, so I even thought about giving today's lecture using Blackboard. Eventually I convinced myself not to do that. But this Blackboard thing is actually a stereotype. It's not accurate at all. I will give you 3 reasons to justify that it's not accurate. First of all, if you go to my office, you will find that my office has a whiteboard, not a blackboard. Okay? And on top of that, as you just heard of, I don't use much. For my research, I don't use Blackboard much. Mostly, I use paper and pencil. If you think about it, it actually makes sense because, as a theoretical physicist, we need to do long calculations sometimes, like may last for hours. If you do it with paper and pencil, you can sit down. That's much more comfortable than writing everything on Blackboard and stand up for a couple hours. Okay? And of course, it's the new millennium. I'm not a caveman, so I do use computers, although it's mainly for text and for typing and for emails. Okay? So I want to explain a little bit why our research, my research of theoretical physics, use a lot of paper and pencil. Okay? I'm not saying that the computer is not important. Actually, computer simulation is extremely important in our research. Personally, I don't write computer code, but I work with many coworkers, and they are experts of computational physics. And their simulation provide extremely important insights and extremely important knowledge that is crucial for our study. And sometimes people even say that computer can answer all the questions as long as we can ask the right question to the computer. So the question is, what is the right question for computers, for physics? Okay? For physics study, in order to ask the right question to the computer or to write the right question to our paper and pencil type calculation, we need to do a couple of things. Firstly, we need to simplify our universe. Fortunately or unfortunately, our world is extremely complicated, extremely chaotic. Okay? There are many things which are just illusions, and some of the ingredients actually are not important at all. We need to throw away those illusions and those unimportant ingredients to simplify the system so that we can focus on the main, most crucial ingredients for the physics problem. Okay? And then we need to translate this most important ingredient into languages of mathematics. We need to translate into mathematical language. And for these steps and for these purposes, paper and pencil are actually extremely handy and extremely neat tool. And after we do this translation, we can either do this calculation using a computer or use a piece of paper. But to find these questions, paper and pencil actually is extremely useful. Okay. And there is another reason why paper and pencil is still a very useful tool in my study, at least for my subfield. So my study mainly focuses on quantum systems. And for quantum systems, interestingly, these systems are extremely hard for computer simulation. And in general, for a general quantum system, the computational cost to simulate a quantum system scales exponentially with number of particles. Okay? So this means that even if we use the most powerful supercomputer nowadays, the cutting-edge technology allows us to accurately simulate a quantum system of a couple dozen particles. Okay? If we don't make any approximations and try to brutally force to simulate a quantum system. A couple dozen is a current upper limit. Okay? And this exponential increase also means if we want to add one more particle to our simulation, the computational cost would at least double. Okay? And we know Moore's law. Moore's law told us every 1 or 2 years, our computational power would double. It means for a quantum system, every 1 or 2 years, we can add one more particle to our simulation. And the projection is in the next millennium, we probably will be capable of simulating a system about 1,000 particles. Okay? But how many particles do we need in a real system? Let's think about this yummy bread from Zingerman. This is actually very yummy Ingerman's sesame bread. I will now try to simulate this bread. That is actually that's too complicated. I will do some simplification. I will try to look at one sesame seed on top of this bread. And I will do another simplification. I will throw out all other degree of freedom, just look at electrons in this system. A number of electrons in this system, unfortunately, I'm not a native speaker, so I don't know how to read this word, but it's roughly this amount of electrons. But I do know that this number is a lot larger than 1,000. So at least in the foreseeable future, we probably will not be capable of accurately and without any brute forcely simulate a quantum system even as small as a sesame seed. Okay? That means paper and pencil will still be our very useful tool for quite some time. But there is a small catch. This small catch comes from actually the topic I mentioned at the top. It's extremely costly to simulate the quantum system. It sounds like this is a very bad thing, but this thing actually can be really, really good for some objectives. Okay? Because quantum systems are so complicated, it's extremely costly to simulate this system. It means that if we can build a computer out of this quantum system, then this computer will be extremely powerful. And in fact, the computational power of such a quantum computer will be exponentially fast, scales with the system size. It means that if we add just a couple quantum qubits to this system, the computational power will double or triple, etc. So with only a couple dozen quantum bits, known as qubits, a small quantum computer with only a couple dozen qubits will beat the best supercomputer. And I want to share one good news for everyone. So from the coming winter semester, the physics department will gradually start some new courses discussing about quantum information and quantum computing. And our first course along this line will become online in the coming winter semester. The first one will be a 400 level courses, but more courses will be developed in the next few years. Okay, so bottom line, I'm a theorist, and I study low energy physics, and these arrows are the topics and the subfield that I study. Okay, so for today's talk, this is a plan. Okay? So I will invite you guys, and will invite every people in the audience to share your opinion about the most important breakthrough in technology, okay? That is either transforming the way we live or has transformed the way we live. Okay? And I want to put a small cap, a small constraint to today's discussion. Let's discuss about something happened relatively in the, not so far in the past, let's say last 2 or 3 or 4 decades. The reason I want to put this constraint is because if we talk about too far back in time, that will be before I was born. So I probably will not guarantee I share right insight about technology and the way we live at that time. Okay? And because I give you 2 constraints, I will also give myself 2 constraints to be fair. So after you tell me what topics you want to hear about, I will explain the physics research behind the thing that made this technology breakthrough possible. Okay? And the 2 constraints I will enforce to myself is I will only talk about the subfield that I study, and I will only talk about the research topic directly relevant to my research. Okay? And the second constraint I will enforce to myself is I will only talk about physics research that has been awarded the Nobel Prize of Physics, which is arguably the most important prize and the most prestigious prize for physicists. And if I have time, after explaining each of these physics, I will discuss a little bit about the current physics research and how does it connect and how it's connected with the topic that I will discuss in the second part. Okay, so now the stage is yours. So anyone want to share some of the topics and some of the breakthroughs that you think are really important? Internet? Okay, great. Where is my chalk? Let me write it down on the blackboard. Oh, over there. Okay, great.
Make sure you repeat.
Sure. Yes. We got one suggestion of internet. So anything else? Let's first compose the list, and I will do it one by one. Quantum computer? Home computer. Okay, great. So sorry, what's that? GPS. Okay, great. That is a good one. Anything else? Digital photography. Sorry, I'm not a native speaker. Can you explain?
Digital cameras.
Oh, digital cameras. Great. Yes. digital camera. Okay. Anything else? Medical imaging. Okay, great. Okay. So I'm pretty sure the list. Sorry, what's that? Lasers. Okay. Okay, so I'm pretty sure this list goes on and on. No, we can keep adding to this list. Any other topic you want to add, or we can start? Smartphones. Okay, that's another very good one. Okay, so I think this is probably a list longer than I could cover because of the time limitations. And towards the end of, oh, wait, sorry, what happened? Oh, great, yes, perfect. Okay, so let's start from, say, internet. Okay. So internet has been there for some time. And one of the key infrastructure behind internet is actually this study. Okay. So this is actually the Nobel Prize of Physics of year 2009. And it's awarded for the study of lights traveling in a medium and the invention of optical fiber. Okay? And for internet, it's actually the main thing is internet makes life so easy for us because we can transfer vast amount of information from one place to another place, even the two places are separated so far away on this planet. For transformation of information, we don't usually think about this too much, but actually there are two speeds we need to talk about when we talk about transformation of information. One is the speed of propagation. That is how long it takes, so after A send out the signal, how long it takes for the receiver B to receive the signal. And of course, this propagation speed, there is an upper bound. Einstein told us the propagation speed of any information cannot go beyond the speed of light. So if you want a fast transmission of propagation speed, you better choose something travels at the speed of light. For example, radio waves and the lights, they both travel at the speed of light. Okay? But there is a small difference between radio wave and the light. They have different frequency. And that has important consequence for another speed of information propagation. That's the so-called data transfer rate. This speed counts how many bits of information one could transfer in 1 second of time. And this data transfer rate is actually controlled by frequency of the waves we use to send this message. And for radio waves, the frequency is typically kilohertz to amhertz. If you turn on your radio, you will see these numbers. That means we can transfer, roughly speaking, about 1,000 or 1 million bits of information per second. But the light has much higher frequency. Typical frequency for light is 300 billion, which means we can transfer this amount of information in every single second. This is actually the reason why optical fiber is such a useful thing. So for every one of us, think about this. When we are watching a movie in our home comfortably in the sofa, our neighbors probably is also watching another movie. And our neighbors, the total amount of information we need to go through this pipe is actually extremely high. For that purpose, light is actually an ideal medium. It has fast travel speed, also has very high data transfer rate. Okay? But light, there is a problem. Light is faster and has a very high data transfer rate, but light can only go along a straight path. And the light can be easily blocked by any object in its way. Okay? So for example, if I want to send a signal to someone in the next room, I can't do it directly using a light because light cannot go through this wall. Okay? And the invention of optical fiber exactly solves this problem. It creates a highway to channel the light to go through this fiber. So in fact, if we send in a light in the fiber, the light just bounces back and forth between the wall of these fibers and going along the fiber in the right direction. That allows us to send the information in the right direction with extremely fast speed. Well, a small side comment, I must say that optical fiber is great for information propagation, but it sacrifices a little bit of the propagation speed. Okay? So I mentioned earlier on the fast propagation speed is the speed of light. And it should be emphasized that's the speed of light in vacuum. Optical fiber is a medium. So when when light moves in a medium, its speed is a little bit below the speed of light in vacuum. So optical fiber, the signal transfers in it slightly and speed slightly below the speed of light. And on top of that, from this figure, we can see the optical fiber, the light goes in a zigzag pattern, not a straight line. This means it takes slightly longer time for the optic signal to go from one end to the other. For our daily life use, this is not a big problem. Like a millisecond or a split of a small piece of a second time difference, time delay, we can't even feel it. But for some situations, this could mean something. There was a movie a few years ago, I think it's called the Hummingbird Project. It is about fast trading, ultra-fast trading. And for that purpose, the project failed exactly because people forgot this small sacrifice, this small problem, optical fiber sacrifice. Okay, now let me talk a little bit about the current research in U of M. So these are two of my colleagues on the U of M physics, Professor Hui Deng and Professor Liu Yanzhao. Both of them utilize light and study how light interact with matter. And Hui actually utilize all kinds of techniques to control light. In addition to optical fibers, there are many other ways to bend the light to control where the light go and go to the spot we want, and even trap light inside the cavity so that all the energy will stay there. And Liu Yan is actually very, very good at utilizing the light to basically shine light on object and utilizing the reflection and the transmission to understand the property. And we are currently working together utilizing materials to control light in search for some exotic fractional topological state, and this fractional topological state actually actually gives us some so-called fractional particles. And the fractional particles is actually a very interesting phenomenon because we know our solid materials are, for example, this table are made of atoms and the nucleus and the electrons. If this table is made of electrons, typically we will say electrons as the building blocks, so we can't have something smaller than electron inside this table. But that's not always the case. For certain fractional topological state, excitations in those states is actually a fraction of this electron, known as fractional particles. And these fractional particles have some very exciting properties, which I don't have time to go into the detail. For example, it can be utilized to perform the so-called topological quantum computing, which is one of the most promising candidates for the future generation of quantum computer. And we are currently studying this material and trying to utilize light and the matter combined together to achieve this goal. Okay, so this is the internet. Home, let's see which is next. Home computer. Home computer is a favorite topic of mine. And you probably know this already. For everything about home computer, and also actually it's probably fair to say for everything behind the whole IT industry, we should thank these three persons. Okay? So these three physicists awarded Nobel Prize in 1956 for the study of the so-called transistor effect. Okay? And I want to mention that Shockley and John Bardeen are theorists, and Barton is more on the experimental side. So among these three persons, I want to highlight John Bardeen in the middle for two reasons. First, John Bardeen is the only physicist who has been awarded the Nobel Physics Prize twice, one for the transistor effect, and the second for explaining the mystery behind the superconductivity. Okay? So he is the only physicist who received the Nobel Prize twice. And the second reason is a little bit personal. So in addition to being a great scientist and great physicist, John Bardeen is also a great leader. He was the physics department head of University of Illinois, where I got my PhD degree. So under John Bardeen's leadership, University of Illinois Physics Department developed an extremely strong physics team in condensed matter physics research. And they developed extremely strong graduate education for condensed matter physics. And the condensed matter physics education graduate program of the physics department in Illinois ranked top 1 among all universities and all institutes on this planet. So personally, I really, really appreciate what John Bardeen did, and which gives the opportunity for me to receive a brilliant education environment and to learn all this exciting physics. And the physics that John Bardeen and the coworkers studies is basically this. Okay? So typically, when we think about the electronic system, we typically will connect two wires to it. One side, the current goes in, that's called source. Another side, the current goes out, that's the drain. Okay? So what John Bardeen and the coworkers asked is a question, out of curiosity, what will happen if we connect multiple leads to this object, And they connect 2 more leads, the so-called gate. And this B, somebody says it stands for back gate, somebody says stands for the bottom gate. I don't exactly sure, actually. I think there are no common agreements. But luckily, both of them start with letter B, so we will call this B. Okay? So basically, what we try to do, or what John Bardeen and coworkers try to do, is try to measure the electric current between the source and the drain, and see whether the current can go through or not. If the current can go through, then it's a conductor. If it cannot, it's an insulator. That's a simple question they ask. And amazingly, whether the system is a conductor or insulator depends on B and G, depends on what electric signal we send in to B or G. For some voltage, electric current from S and D goes through, so it's a conductor. For some other voltage, it doesn't. And if the current goes through, it's a conductor, we call it 1. If it's an insulator, current cannot go through, we call it 0. That's actually 1 and 0 behind every single computer. Okay, so for all our computer chips, it's millions or billions of these small transistors. And the study of Shockley and Bardeen and the coworkers is really the key behind this technology. Okay? And currently, in our physics department, our colleague, Professor Charlie Kordak, is actually extremely good doing this multi-leads measurement. So he connects multi-leads to an object and study electric current. And the reason he wants to, this multi-lead structure for Professor Charlie Kordak allows him to do some very exotic and fancy measurements. So typically, when we have a piece of object, we try to measure, say, conductivity. We try to measure electron flow from inside this object. Typically, when we go send this electric signal goes through this system, if we think about it, some of the current will go through the bulk, but there will be some current on the surface. Most of the time, we don't care. We just care about the total amount of current that goes through the channel. But in some study, for example, in a study of topological state of matter, whether the electrons that go on the surface or go in the bulk makes a big difference. And this multiple leads technique Charlie created actually allow us to differentiate electric current going on the surface or going through the bulk. He can tell, he can split the contribution into 2 different parts and understand the motion of electrons on the surface and at the same time in the bulk. And these are figures from some of the papers we studied together, and we use this technique to study some topological states. If I have time, I will come back to this topic later. Okay, so that's a home computer, and the physics behind it is the transistor effect. GPS system. Okay, so GPS system is actually one of my favorite inventions. I remember like 20 years ago when I just came to the US, I go to a field trip with my friends. We first time driving a car, going many, many different cities like DC and New York, etc. And in that trip, we always need to put one of my friends sitting next to me as co-pilot when I'm driving the car. And his job is to read the map and tell me where I should take the turn. So let me find the slides. Where is the slides? Just 1 minute. Here. So the GPS system is basically a bunch of satellites. These satellites are kind of like radio stations, but this radio station only send 2 signals. They don't send music, they don't send news, they only send 2 signals. One is time, that's based on a clock carried by the satellite. Another is the information about their own location. Okay? And because the satellite has some distance away from the receiver, then there is a time delay. After the satellite sends out the time signal, there will be some time delay when the receiver received it. And the time delay is distance divided by speed of light, because this radio signal travels at speed of light. And by measuring this time delay, we can measure the distance between the receiver and the satellite. If we have multiple satellites, we know the distance from every single satellite, and we know the location of the satellite, then by some geometry, we can calculate the location of the receiver. That is a GPS system. And in this whole procedure, the most important thing is time. We need a very accurate measurement of time. This is because the signals transmit at the speed of light, which is very, very fast. Even a tiny bit of error in time will cause a huge, huge error in distance. Okay, so we need extremely accurate measurements of time. And the solution to this extremely accurate measurement of time is is actually the so-called atomic clock. That is the Nobel Physics Prize in 1989. So the atomic clock is actually not fundamentally different from not this watch, from the watch we used to wear with quartz in it. So in the old days, all the watch has a quartz in it, and the quartz vibration produce a very, very accurate frequency, and that is how we can accurate time measurements. But that accuracy is good for daily life, but far from enough for GPS locationing. And in order to get a more accurate time, the atomic clock, we use actually atoms. So quantum physics tell us atoms has actually quantized energy levels. These energy levels give us very precise frequency of oscillation, much more accurate than quartz. But the problem is atom is too small. We can't directly measure the frequency of one atom. So a very smart design is then introduced, utilizing this oscillation of atom to form a feedback loop. And this feedback loop is a negative feedback loop. It basically compares oscillation frequency of this atom with quartz. And if the quartz is oscillating too fast, if the comparison comes out saying the quartz is oscillating too fast, then it sends a signal to slow down the oscillation of the quartz. If it's too fast, then it sends a signal to make it oscillate a little bit faster. We still measure time from this quartz, but because of this atomic levels, this quartz now measures time much, much more accurate. And that is the technology behind the GPS system. Okay, so at the beginning of the talk, I said that I will only talk about Nobel Prize physics research award Nobel Prize, and I will only talk about subject that I directly study. Actually, I lied a little bit. So on the next slides, I will show another important technology, really, really important behind the GPS, but it's not awarded a Nobel Physics Prize. That is actually from Albert Einstein. Okay, so Albert Einstein only awarded the Physics Nobel Prize once in his life. And the topic he got awarded for Nobel Prize of Physics is the photoelectric effect. And this photoelectric effect is actually also extremely important actually for all the solar panels we use in our home or in the International Space Station. It actually is this photoelectric effect is the foundation of all the solar panels. Okay, so that's Einstein's Nobel Prize. So although Einstein was only awarded Nobel Prize once, he deserves at least another 6 or 7 Nobel Prize. So basically, the research subjects he did, the knowledge he contributed, leads to some predictions that other people who proved these predictions got awarded Nobel Prize, but unfortunately Einstein didn't get. Okay? And another thing I want to mention about Einstein is that Einstein lives in the early days, we all know that. And at that time, these 3 branches, high energy, low energy, and astronomy physics, it has not really been formed. So at that time, Einstein actually has a very good environment, he has a resource, and he has knowledge to study all the subjects. And importantly, he made a significant contribution to all the 3 subjects. We all know special relativity, which is the foundation of high energy physics. And we all know general relativity, gravity, and gravitational waves. This work actually is the foundation of astrophysics and cosmology. And most importantly, his prediction about gravitational waves got awarded Nobel Prize a few years ago because people really proved that Einstein was right. His prediction is actually right. Okay? And in low energy physics, Einstein also made a lot of really important contribution. I mentioned the photoelectric effect. And he also studied the theory of so-called stimulated emission. This partially takes out laser, partially, because this stimulated emission is actually the foundation how laser and the maser works. Unfortunately, Einstein didn't get awarded for Nobel Prize for this foundation of theory, but people who followed his theory to create a maser and the laser got Nobel Prize in 1960. And he also predicted a very exotic, very interesting low energy state. So he said that if you cool down a system made of bosons to really low temperature and very low energy, you will see a very interesting new quantum state of matter. Now we call it Bose-Einstein condensate. And he didn't get Nobel Prize for this, but this prediction, or people who verified this prediction, got the Nobel Prize in 2001. Okay? And he also studied Brownian motion. So basically, he looked at the very tiny particles floating in water and their motion. And by looking at their motion, Einstein proved the existence of atoms way before we can really see atoms. And the experimental study who look at this motion of the pollens got Nobel Prize, but unfortunately, Einstein missed his share. And his study about the so-called EPR paradox actually is directly relevant to the Nobel Prize of this year, just announced a couple months ago. And the topic about, so we're talking about GPS. So instead of discussing about all his discoveries and all his important contributions, let's focus on this one, special relativity and the general relativity. These two studies are extremely important, but Einstein never got a chance to be awarded Nobel Prize for this. And this two effect actually is another important physics behind the thing of GPS. Okay? From special relativity, Einstein told us that the clock ticks at different speed. A moving clock actually ticks slower than a regular clock, a not moving clock. Okay? This is a so-called time dilation. And the gravitational field also causes time dilation. Combine these two effects together, because GPS satellite is moving relative to us. We are not moving on ground, the receiver is not moving, but the GPS satellite is moving, and we have different gravitational field. That means time on the GPS, clock on the GPS, ticks at different rate from us on Earth. Okay? That difference is not huge, but it's there, and it accumulates. So after a couple months, this difference will become really, really huge, and the time measurements will get a huge error. And that huge error means, as I mentioned earlier, the location will be totally wrong, differs by hundreds of miles. Okay? And luckily, Einstein already told us this. We already know this effect before the GPS satellite is launched. So in the design of GPS system, this physics is already taken into account in their design. It's properly compensated. If we didn't know this, if Einstein didn't tell us about time dilation, if we didn't know this knowledge, and then after we send the satellite into space, after a couple months, we will mysteriously find that nothing is working. And probably it will take years for people to figure out what's going wrong and how to compensate that. But at least it will delay the system for, let's say, a couple decades probably. Okay, so that's the physics behind behind GPS. One thing I would like to highlight here is that, obviously, when Einstein is thinking about this time dilation, he is not thinking about making a precise time measurement or making a GPS system. This is a so-called curiosity-driven research. Okay? It means this study is not about application. We're not thinking about application. We're thinking purely about our curiosity. A curiosity about exploring uncharted territory in research, and curiosity about finding the reason behind some puzzles we never understood. Okay? And interestingly, although the goal, the objective of this study has nothing to do with application, with usefulness, the knowledge generated by this study turns out to be extremely useful in applications. So sometimes I wonder, this is so strange. We are not looking for applications at all. We are not looking for something that will change our life, daily life, in our research. But the knowledge generated from this research sometimes turns out to be really, really useful. Okay, I think I'm running out of time, so I will hijack the topic a little bit. So instead of talking the digital camera, I will come back to this topic slightly later. Let me jump to another topic and I want to discuss today. That is about the smartphones, because I really like my smartphones. Okay, yes. So behind the smartphones, there is one very important research behind smartphones. That is from Dejan. Okay? Dejan is a theoretical physicist. And from this picture, I can't see quite clearly what's in the background, but from the dust, I guess it's another blackboard. Okay. And you may notice that in Einstein's picture, the background is also blackboard. It seems it has been there. It's an old tradition. Okay. So Dejan is awarded Nobel Prize of Physics in 1991 for his study about liquid crystals and the polymers. Okay. So what is liquid crystal? So before we talk about liquid crystal, let's talk about some daily life experience. We know that if we increase the temperature, start from a solid, say this very nice snowman. If we increase the temperature, it will start to melt, and that's known as the melting temperature. If we go beyond the melting temperature, this gentleman will melt into a liquid form. If we keep increasing the temperature, we will hit the so-called boiling temperature, and after that, we will get a gas. The liquid will turn into a gas. So for generations and for centuries, it is a textbook doctrine says that, there are three states of matter: gas, liquid, solid. That's a doctrine. Until 1888. Okay? So in 1888, people discovered something different. So in some materials, people showed that if we increase the temperature, it melts into a liquid. So far, so good. And if we keep increasing the temperature, we get boiling. So far, so good. But then, after boiling temperature, if we keep increasing temperature, we get another liquid, not gas. And keep heating up, another boiling, then another liquid. Then keep increasing temperature, eventually we get gas. Okay, finally, gas is there, okay? So somehow there are 3 boiling temperatures, 3 mysterious liquids. Instead of turning into gas, this liquid just keep turning to another liquid. And that puzzled people for a very long time. And it's De Jong who really explained the theory, formed the theory behind the thing. It turns out that among these 3 liquids, the top one is our liquid, the liquid we call liquid. The other 2 liquids has 2 different names. One of them is called pneumatic liquid, another is called smectic liquid. The name is not so important. But pneumatic and smectic liquid together, and also some other similar states of matter discovered later, they combine together is known as liquid crystals. Okay? And what's really going on? Okay? So because this liquid state is really the mystery, let's focus on these liquid states. Temporarily ignore the gas and the solid and just look at these 3 liquid states. It turns out that the real reason for this interesting phenomenon is because inside these materials, the molecules has a very special shape. It looks like a cigar. It's like a rod. Okay? So in all these materials, we have cigar-shaped molecules. Okay? And if we have a liquid made of these cigar-shaped molecules, this liquid, the normal liquid phase is similar to our water. These molecules moves around, pointing in the random directions, and moves all over the place. In the pneumatic liquid, when we reduce temperature, these cigars will be pushed together. The packing will get denser and denser. When you pack a bunch of rods together and you try to push it, you know what will happen. This cigar will line up to save space. And that turns out to be the origin of the pneumatic phase. So in the pneumatic phase, these cigars are still moving around, but they form this aligned structure. They all point into the same direction. It's not surprising at all. In fact, nature shows lots of these examples. For example, if we look at a school of fish, if we have a very dense school of fish, sometimes fishes do that. If we have fish do that, if we have a very dense school of fish, neighboring fish will swim in the same direction to save space, so they will not bump into each other. This is exactly the same physics. And if we keep reducing temperature, then these cigar-shaped molecules, when they become denser and denser, they form layers to save space. And one layer on top of another, etc. That's the smectic phase. Okay? And the main focus of this part is the pneumatic phase. This pneumatic phase is actually very much like window blinds we use, okay? Because it has a direction. And interestingly, the direction of these rods can be turned using an electric field. So by applying electric field, this rod will align with the electric field. If we turn the electric field, this rod will turn accordingly. That means we can use the electric signal to control open and shut of this window blind. That's exactly what happened in a so-called LCD display. LCD display is actually liquid crystal display. That is actually using this physics. Okay? And more precisely, inside each pixel of LCD, there are actually 3 of these little tiny blinds because we have 3 primary colors. Each one controls one of them. That's how the liquid crystal display works. Okay? If we compare liquid crystal display with the display I used to call display when I was still a young gentleman, when I was still a young gentleman, display looks like this. So this was the iMac back in 1998, and this is the latest iMac version. And the main difference is this one uses a so-called CRT display. This one is a liquid crystal display. If we compare them, obviously we can see the liquid crystal display is a lot thinner. Okay? So for personal computers, this probably doesn't make a very big difference. It looks a lot nicer to have a liquid crystal display, but the CRT display, we can live with it. It just takes a bit more space. But for smartphones, that's not the case. Okay, for smartphones, the most important feature, or most visible feature of smartphones that distinguish it from the old generation of cell phones is a big display that keeps getting bigger. Okay? And to have a big display for a cell phone, the CRT technology just can't be used. If we use the CRT display to make a smartphone, it will be at least 1 foot thick. Okay, it will be a ball, it will not be a phone. And another big problem about CRT displays is it costs a huge amount of power. If you use a CRT display for cell phone, it will not last long. It will just like 10 minutes or so. Okay? So liquid crystal is really, really the technology made the smart devices possible. And thanks to John, actually, he made he is actually the real person who made this crucial contribution to this development of technology. One thing, again, I want to mention here is when John studied liquid crystals, he is not thinking about making a better display. I'm pretty sure he's not thinking about it. I didn't ask him because he passed away before I got the opportunity to chat with him. I didn't ask it, but I'm pretty sure he is not thinking about making a better display. Because at that time, liquid crystal was not even considered a good option for display at all. So the reason driven John to study this system is, again, curiosity. Okay? So John is curious about why there are so many different liquid states. Why the liquid doesn't turn into a gas after boiling temperature? This is, again, another example of curiosity-driven research. And we are not pursuing applications. We are not thinking about applications at all. But eventually, it leads to something really, really important for our daily life. Okay? And speak of the continuation of this research in the physics department, I would like to highlight this is actually my thesis study. And if you look at the title, quantum liquid crystals. Okay, so basically, when I was a PhD student, the main focus of my thesis study is study a quantum version of the John's liquid crystal system. Although I study a little bit of liquid crystal in my research, speak of continuation of the John's research, I need to mention one of my other colleagues, Professor Xiaoming Mao. So I mentioned liquid crystals, all the interesting physics comes from packing of rods. Okay? One of the research area Professor Xiaoming Mao study is packing of other shaped object. Say, for example, tetrahedrons. If you have a bunch of tetrahedrons and form a liquid and pack them together, what will happen? It turns out that this question is way more challenging than packing of rods than liquid crystals. Okay? And the reason is because for rods, when we try to pack them, there is always optimum packing, that is to align them. Okay? For tetrahedron, if you try to pack them, there is no optimum way. No matter what you do, there will be some huge gaps, and you cannot fail. So there's no obvious way to packing it. And to understand this packing, it turns out we need to go to curved space, just like what Einstein did in special relativity. By going to curved space, everything has, actually tetrahedron has a perfect packing. We can find exactly what's the best way to pack it, and then we project back to our flat 3D universe. And by going through that procedure, this is studied by myself and Professor Xiaoming in a theoretical study. And from our theoretical study, we find that by projecting back to our flat space, this packing of tetrahedron leads to helical structures. It's kind of like DNA and helical. So it's actually quite interesting because tetrahedron that is straight. It's all straight lines. It don't want to curve. There's nothing obvious there. Gives us bending structure. But when we pack them, turns out that they want to form this curved helicoid. And the reason they want to form this helicoid is exactly because we need to go through this curved space. In a curved space, everything is packed nicely with straight lines. But a straight line in curved space, when we go back to our flat space, it becomes a curve. That's where this helicoid structure forms. And amazingly, this is indeed what happened in experiments. Our experimental colleagues from the engineering school showed the packing of tetrahedrons. And indeed, this helicoid is what they found. OK. So that is let me look at time. OK, I think I'm too ambitious about my talk, and we are almost running out of time. So I will not have time to discuss about my own research on topology in quantum systems. But I do want to talk one more thing before we conclude. That is about the nature of this curiosity-driven sorry. Let me go through this. Let me show this list really quick. OK, so there are some other topics we don't have time to cover. But this is a list of Nobel Prize physics awarded for low-energy physics. And I highlighted some of this yellow area that's either directly related to my research or has a really important impact in our daily life. From this, you can see some really familiar things. The invention of blue LED, that's LED light, LED lighting we use, CCD cameras. So this is actually the technology behind the digital photography. And atomic clocks, I think there is another one, the invention of laser, the foundation of laser, and NMR. This NMR, the Nobel Prize Physics in 1952, is really the foundation for the imaging technology we use nowadays in hospital. So X-ray can see our bones really, really nicely, but NMR gives us technology to see the tissues and even real-time flow of blood in our body. Okay, because I'm running out of time, so let me mention one more thing before I conclude. Okay, so in fact, if we look back to all the examples I discussed today, there is one thing in common. All this research are driven by curiosity. Okay, so like when Einstein thinks about special relativity, he's not thinking about making a precise measurement of time. When De Jonge is thinking about liquid crystals, he's curious about why there are these liquid phases, not about trying to make a better display. And this curiosity-based driven research purely focused on, purely driven by our curiosity, the human nature of curiosity to explore uncharted area, to find the answer to questions we don't puzzle us. This curiosity-driven research, although we don't think about usefulness in these studies, it turns out knowledge we find from these studies actually turns out to be of the greatest useful. It changed our daily life. So when I was a student, I keep asking myself why. Because when I was a grad student, I know what roughly physics research looks like. I know we don't think about the replication, but why somehow these studies really, really have a huge impact in our daily life? Well, there could be many, many reasons. So some reasons I come up with when I was a graduate student is, it's like this. Maybe it's because, sometimes if you're not looking for something, the things you really, really want will just pop up. Maybe that's the reason. Or maybe what the Tai Chi master said was right. If you want to go up, in Tai Chi, you first need to bend down and before you go up. So if you want to find something really useful, you need to first search for something maybe not so useful. Or maybe search for pure knowledge and the search for usefulness may not be actually contradict to each other. Maybe they are the same thing. They are just two sides of the same coin. Okay? But there must be some other reason. Okay? So I want to mention one other reason that that I feel might be really behind this puzzle, behind the thing, is about the thinking out of box. Okay? When we talk about revolution or like say leaps in technology or leaps in almost any area, a very important ingredient is to think out of the box. If everyone else is already thinking about that and you try to follow, probably that will not lead to a huge jump or huge revolution. And how do we jump out of the box? Well, the most efficient way to jump out of the box is not to harm the box. Okay? If you don't harm the box, not confined by the box, then you're already outside the box. In some sense, application is a box. Okay? So application is really, really important. Invent something, change our daily life, improve our life is really, really important. But if we think about application every day, we will forget outside of this box, there is a huge universe. And that huge universe is uncharted, and there are lots of mysteries wait us to explore. And the curiosity-driven research does exactly that. Okay, we don't think about the box. We're not inside the box. We're just searching for interesting things in our universe. And some of those knowledge turns out might be really, really important. Okay, I think I'm running out of time, and I do want to leave some time for questions. So I will jump to another chunk about my own research about topology, and directly jump to the last slides. And thank you for your attention. And I want to conclude my talk with a slogan on our department T-shirt: "Physics is for everyone." And thank you for your attention.
Thanks very much, Kai, Professor Sun, for that very insightful and entertaining presentation. So we have a Q&A session. This is tradition for Saturday Morning Physics. I have to apologize that I did not introduce that at the outset. We welcome questions from the audience. If anyone grabbed a card or wrote their question down, if anyone would like in the next several minutes to email to this address your question, physics@umich.edu, and we'll also take questions from the audience, which I'll repeat, okay? So, I'm going to start, actually, with a couple of questions that came in during the lecture, because some people are savvy to this. Actually, how often do you erase your, well, not blackboard or whiteboard, but how often do you actually need to use an eraser on your paper? Or do you use pen?
Right, so actually this answer might not be very explanatory friendly. I don't use the eraser. If the calculation is something wrong, I will just throw away the piece of paper and get another. So, for people whose office is adjacent to me, they probably notice every couple of weeks, I will have a pile of paper dump into the recycle bin, and that's a paper of calculation that turns out to be not so exciting, and I'll push it away. And all the exciting ones, we keep a very nice record and a digital record of those calculations, and post it online or share it with everyone, the general public.
Great. Just one more thing along the lines of levity. Does anybody know? So Professor Sun showed 1 with 27 zeros. I don't know if anyone counted them, or the sets of zeros. Does anybody know what that number is called? Yes?
I would prefer using a K number. So a K1 would have to be 1,000, K2 would be 1,000,000, K3 would be 1,000,000,000. That way you would know very instantly what that number would be.
And the answer is? Sextillion, I believe, right? Anybody agree with that? Okay, good. All right, well, that was fun. Okay, so here's a question, which is actually, how much is light slowed in the transmission of light through these optical fibers? Is it big, major, or not so?
Actually, this is a good question, and this is a question I could not answer. The reason is because I'm a theoretical physicist, and some of you may know, some of you may probably not. So for theoretical physicists, the first thing when we do the calculation is to convert all the units to 1. So everything is 1. So in our calculations, there are only 3 numbers, 1, pi, and e exponential. And because they simplify the calculation a lot. And then after we finish our calculation, we really chat with our experimental colleagues. We try to dig the unit back and add all this physics constant back. So for a precise number, unfortunately, I don't have that, but I'm pretty sure my colleagues, some of my experimental colleagues in the in the physics department knows this very well.
Okay, cool. Can you explain why quantum mechanics is actually needed for condensed matter physics?
Oh, yes, that's a great question. Yes, so in condensed matter physics, basically one of the main focus of study is materials, all kinds of materials, like this table, materials we made our airplanes, our cars, and our computer chips, etc. For material property, actually, the most important ingredient that dictates the property of material is the motion of electrons inside this material. Okay? So electrons inside material and how do they move dictates material property. Decide whether the material is an insulator or conductor, decide whether it's a superconductor or not a superconductor, it's a magnet or not a magnet, decide it's soft or hard. So in order to understand any physical property of any materials, we need to look at the motion of electrons at least. And electrons are quantum particles, and their motions are governed by quantum mechanics. And that is one of the main reasons why in condensed matter physics and why we study actually any systems, any materials, we need the quantum ingredient in it to correctly keep track of the motion of electrons. And, and another part I want to add to this question is not directly related with this question is that to understand the motion of electrons is extremely important for the understanding of materials. And that is actually also an experimental challenge of condensed matter physics, because electrons are hid inside a piece of solid. We cannot touch it. If we cannot touch this electron, we cannot precisely measure its experiment. To measure the experiment, we need some trick to get the velocity, the energy of these electrons, and the spin, that's the rotation of these electrons, without really touching it. And there are several experimental techniques. I don't have time to go through that part of my talk today. One of these techniques is called angle resolved photoemission, and we have actually 2 very extremely good colleagues, expert of these areas. One of them is Jim Allen. He is a pioneer of this technology. Another is our latest hire in the physics department, Nahong Zhou. And this interesting technology actually comes from Einstein's photoelectric effect. The idea is exactly what Einstein said. We shoot a photon, kick out the electron, then we measure the electron, we kick it out. And with this information, we can back out the information about what the electron looks like before it's being kicked out. So the electron is the main reason why quantum physics is needed in my study.
Are there any follow-up questions on that from the audience? Yes. So if you would call out the question, and then I will repeat it.
There is one box that people use, people who are in powerful positions, and that is to develop physical principles into military technology. And anyone who is working in theoretical physics and is motivated by curiosity, as you are, is in the predicament of possibly developing an idea which might be converted into its destructive potential. I'd like to just discover your reaction to being in that potential predicament.
So the question or comment is that among the practical applied outcomes of curiosity-driven research are military applications. And how do you feel about that?
Yeah, this is a very great question. So, there are lots of examples of that type. For example, nuclear bombs. It was discovered out of curiosity, and it turns out to be one of the most powerful and devastating weapons that human beings have ever developed. There is always a possibility some of the knowledge we discovered out of curiosity may lead to some really destructive applications. And the main reasons are twofold. First of all, the curiosity-driven based research don't think about application at all. We don't care about applications. We just thinking about curiosity. So we will not be able to predict what this discovery will lead to, where it will be used for. And secondly, honestly, military is always very hungry for new technology and new development. They try to digest all the useful new development in technology and in science and use it for their purposes. So I think and for our research driven by curiosity, we publish all our results to the general public, and everyone can read our papers. It's available online, free and open to everyone. And from our side, we can't prevent someone who read this paper and come up with an idea who may lead to disaster consequences. I think for that purpose, the most efficient way will be through some, through the leadership of the country and the collaboration of international communities to try to confine the application after the development of the knowledge. The knowledge itself is innocent, but how to use this knowledge is beyond what the physicists can directly control.
Okay, we're on the big question part of this. There are some more detailed questions. So this is sort of, okay, I'll come back to this. You have a wide range of research interests. How do you manage to find and integrate the knowledge from so many different branches of physics into your results, your physics results?
Great. So yeah, to answer this question, let me show one of my slides again. Where is my cursor? Oops. I can't see my mouse cursor. Sorry, here, find it. So actually, to explore a broad range of topic is not something unique to myself. Actually, a lot of physicists does that. For example, this is one slide I showed earlier on. If you look at the research profile of Einstein, Albert Einstein, you will realize how broad that is. He studied things small as pollens in water, universe, and high energy particles moving at the speed of close to the speed of light. So this, I will say, is a very luxury thing that we theoretical physicists could really, really enjoy, because our research only need paper and pencil. So for all these research areas, the fundamental material requirement is the same. It's paper and pencil. So there is no limit from the material side to limit the scope of our exploration. For theoretical physicists, the only limitation in the research area is curiosity. And if you have enough curiosity to explore a new area which you have never explored before, and if you have the willingness, want to sacrifice some time to learn knowledge about that new field and try to make some big discoveries in that field. I think this is one thing I really, really like and really, really enjoy as a theoretical physicist. And this is actually part of the reason I become a theorist. The other part of the reason is because I always break things in experimental labs, which is part of the reason why there's no demo today.
Okay. Thank you. Here's a not quite so big, but really interesting question, which is why was the invention of the transistor a problem that theorists need to solve as opposed to
Yes, this is a great question. So the invention of a transistor, it may look like it's an invention, it's a technology invention, but actually the principle behind the thing was actually a physics problem. And to the time where the transistor was invented, we physicists actually don't have a lot of detailed knowledge about the motion of electrons inside the solid material. So if we try to invent a transistor with our current knowledge about condensed matter physics, it will be just a very simple procedure because we already know how electrons move in a solid and how to control the motion of electrons moving in a solid. And to the time where Shockley, Bardeen, and co-workers developed this transistor, they have no knowledge about, they have very little knowledge about how to control the motion of electron and even how electron moves in a solid. So the procedure of development of the transistor is not only a procedure of inventing a new electronic device, but to understand the principle that governs the motion of electrons. And I didn't have time to go into the details why this controlling of the gate voltage can turn a material from insulator to a conductor and backwards. Why there is this controlling can flip 1 to 0. And all those knowledge was developed actually by theorists, Bardeen and Shockley, in close connection, in close collaboration with the experimental colleagues.
Let's go to the audience to see. Yes.
Can you explain something at the beginning of your talk that was a mystery to me? You talked about the frequency of something determined the capacity for transferring information. And that's not obvious to me. Can you explain that?
Right, yes.
And let me repeat that, if that's okay. So the question is, and I think you emailed this as well, at the beginning of your talk, you talked about how frequency affects the rate of transmission of information. Could you explain that in more detail?
This is a great question. So instead of a careful theoretical explanation, I will try to explain this using a cartoon. Okay? So basically, this is the same thing no matter we transmit information using electric waves or sound waves. So for example, let's talk about sound waves. So we talk to each other, and we can understand each other. And obviously, some information is passed. Is transmitted. And the way we transmit information through, say, sound waves is to change the frequency. So the tune, and to change the frequency of our vibration of our throat, we send out a wave with different frequency, and the ear pick out this different frequency, and using this frequency information to decode the information sent by the source. And the radio waves is exactly the same. So we change the frequency or the amplitude, and through modifying the wave, we pass the information. And in order to change this frequency, we can't change the frequency a lot based on its original frequency. So if the wave actually oscillates very, very fast, we can change the frequency in a wider range, or in a wider region. That allows us to actually send more signals. So basically, another way to understand this is to measure the frequency. To know the frequency of the wave I receive, I need to measure at least one periodicity. It means to pick this signal, I need at least wait one periodicity of this wave to pick this signal. That is actually the upper bound of transmission information limit. You need this time to measure it. If the frequency is very, very high, which means the periodicity is very, very short, you need a very short amount of time to pick up this signal. But the frequency is very low. You need to wait longer time to finish listening to this period to get the frequency and get the information coded in it. So I hope that this answered the question.
Yeah, that's all right. Thank you.
Okay, great.
Here's a question about quantum computers, which is, are they only suitable for specific problems, or can you solve any problem that a computer would solve with a quantum computer faster?
Yes. That is a great question. So for classical computers, we usually do not distinguish this concept. For quantum, actually, in fact, no matter it's classical computer or quantum computer, there are two types of computers. One type of computer called the universal computer or universal computation. Universal computation means you can solve all the problems. Actually, that's actually something actually mathematicians told us a long time ago in the early days of computer technology. Okay? And Turing was actually one of the most important person who made a significant contribution to the proof of that theorem, the so-called universal computing. And there are also some so-called specialized computers. Those computers are not for solving every single possible problems. They are designed to solve some specific problems. When we talk about the computer we use in our daily lives, for example, Mac and PC, those computers are universal. So they are supposed to be able to solve everything. For our daily life, our computer we use, we usually don't even talk about specialized computer. But for quantum computer, it's actually still under development. And for quantum computers, the specialized quantum computers, there has been a lot of progress in there. And there has been some very successful specialized quantum computer who can do very specialized things extremely fast, better than any supercomputer in our we have nowadays. But the other side of the universal quantum computer, they are very important progress, but I think we are not there yet. We are close to making a very, very extremely powerful supercomputer, universal quantum computer. But there's still some efforts where we need some fundamental knowledge, and also we need some knowledge from the engineering side. And combined together, this effort may lead us something there. The main challenge in the development of a universal quantum computer is related with the exponential increase I discussed earlier. Because the quantum computer, the reason it's so powerful is because the computational power increases exponentially when we add one more qubit, or we add more and more qubit to the computer. But as we add more and more qubit to the computer itself also becomes exponentially more complicated. So how to add more qubit to the quantum computer and maintain the quantum coherence and maintain the right, we got the right calculation result, no errors in our calculation is actually another challenge. And we are not there yet, but for universal quantum computer, we are moving closer and closer to the so-called quantum supremacy.
Super. Here's a couple of questions, really, I guess, about liquid crystals. First, was it a paper and pencil problem? But second, why is it so fast that it can be used for displays, et cetera?
Right, yes. So for liquid crystal, actually, it's a combination of pencil and paper and the computer simulation problem. So, and at the time of the Dejean, we don't have a very clear understanding about the liquid crystal itself. And for the development of fundamental theory, Dejean relied a lot on calculation for paper and pencil, and the field theory, etc. That's the same technology we use, and same theoretical technique we use to the study of quantum system and the high energy physics. Okay? But after we understand the fundamental principles doesn't solve all the detailed problem. For example, exactly like how fast these molecules rotate. Fundamental principle will not be able to tell you that. To obtain this part of information, computer simulation actually plays a very, very important role in liquid crystal. So liquid crystal, at least the liquid crystal Dejean studied, are very big molecules. When molecules are big, they are less quantum. They're actually pretty much classical. A liquid crystal system is actually classical. It means computer can very efficiently solve those problems. There is no exponential, cost increase when we have more and more molecules. So, computer simulation actually play a very important role in the liquid crystal, especially for the search of, detailed physical properties like the rotation speed. For the second part of the question, why it rotates so fast, this is exactly because these are molecules. We know that the bigger object, the more inertia the object it has. So it's harder to change its direction. The molecules are tiny and very, very light. It means that even a very small kick or flip it in a very fast way. So that is exactly the reason why liquid crystal display has such a fast response, because these are molecules. We can rotate them really, really fast. In principle, if we can achieve the same thing with smaller particles, then we should be able to increase the speed even further.
So I have somewhat of a summary question, which I'm also going to make it a little more specific. So the question is, with the current research, what do you think the next transformational, curiosity-driven to technological and applied thing will be? And is it perhaps non-Euclidean crystals?
Yes, this is a great question. So yeah, so the honest answer to this question is I don't know, and I don't care. The reason is because the research we are doing is curiosity-driven. So whether this study has potential important applications or not, and if it is, when it will take place, it's not part of the thinking when I try to study any systems. But that does not mean I never been curious about what potential applications these studies could have. Actually, I prepared some slides to talk about potential applications, but I decided to skip them. And the main reason is because I think I was too ambitious. I prepared too many slides because I don't know what list I will receive. So I prepared a bunch of slides for almost every single topic that could arise from the audience. So I think I only covered about 1/3 of the slides I prepared. So maybe I can answer this question by giving one example. So for example, the non-Euclidean crystal stuff. Okay, so this packing of the tetrahedron, for example, we know that we need to go to a curved space. The curved space is also known as a non-Euclidean space. And this packing, this study we showed from the theoretical side, and in good agreement with experiments, we find that the packing of very simple shape, like tetrahedrons, could form very complicated structures like this helicoid, like DNA. Okay? If we think about this, this is exactly what living creatures does. It's exactly what happened in our cells. Okay? Living creatures pick up very simple molecules and then connect them together to assemble them into some very complicated structures and can perform very complicated features. Okay? This topic is related with engineering concept and the engineering technology of so-called self-assembly. Self-assembly basically means you dump a bunch of parts there and let them organize themselves and combine themselves together into something. So for example, nowadays when we want to build a house, we need to get all the limbers and all the stuff, and we need to build it. But wouldn't that be wonderful if we just dump a bunch of limbers there and they connect themselves together and they automatically form a house? That is actually the concept of self-assembly. Okay? This may like a daydreaming, but it's not totally impossible because we have already seen some of examples. Very simple parts can connect themselves and assemble themselves into something really, really complicated. Okay? So potentially, this study can help us understand the principle of self-assembly and eventually may lead to some useful applications. For example, in some sci-fi movies or novels, you probably will see this concept of micro-robots. So for example, we can have very, very tiny robots of size of a virus, and then we inject these robots into our human body, and the robot will hunt down the virus and cancer cells and kill everything that harms us. And if we have that technology, the pandemic will never be a problem. We can just let this robot kill every single virus in our body. And if we want such a small size robot, how to assemble them might be problematic because we want to assemble something at very, very small scale. And on top of that, if we want a macro robot to kill our, say, for example, coronavirus in our body, we probably need more than one. There are many cells, many viruses. We probably need an army of millions of these robots. So we need to find a way to mass produce these robots. And for that purpose, self-assembly might actually be a very useful and crucial technology. Just imagine we have a bunch of small nanoparticles and dump it there. They will connect themselves together and form a complex structure like a robot. So potential applications, sometimes I do wonder, and I hope this one example demonstrates part of the potential applications that may realize, who knows, in the next couple hundred years or a couple decades.
That's neat. So if I could, I wanted to mention something about medical imaging. Two things, really. So you don't need to back up, but the first Nobel Prize was in 1901, I believe, to Röntgen for the discovery of X-rays. And it's a long story, sort of. But one of the fascinating things to me about that was, at the time, the news went out on telegraph, as I understand it, and it was months or less before it's actually being used in hospitals for medical diagnostics. And then NMR was discovered just after World War II by groups led by Purcell and Bloch at Harvard and Stanford, respectively, based on the technology that was developed in World War II for radar. Okay, so the high frequency and high powered work that they did. And it was maybe 40 years before MRI. It was perhaps a decade or more before it started having a big impact in chemistry and pharmaceuticals and so on. So there's different stories, and there's even ways in which it went the other way. The applied research in World War II led to NMR and that expertise. So there's a comment that I wanted to also have you respond to, two of them. One of them is that the fundamental physics, understanding the fundamental physics, lets you know in principle what's possible. And then beyond that, it's work, right? Engineering. How would you respond to that comment?
Yes. So yeah, this is actually a great point. So in the physics research, of course, our ultimate goal is to understand the fundamentals. But at the same time, there are lots of other complications and lots of not so fundamental things we need to worry about in our research. The research are entangled together. And I want to highlight that not only the research of fundamental and not so fundamental physics are entangled together, the discoveries about fundamental physics and not so fundamental physics are also entangled together in many cases. This is because the research are exploring about the unknowns. We are exploring the unknown universe and unknown phenomena. And actually before, when we study something, we will never know the outcome. If we know the outcome, that would not be called research. We already understand that. Because of this uncertainty and this unknown nature of our research, sometimes things we believed to be trivial, to be just noise, turns out to be something extremely, extremely important and extremely, extremely fundamental. So, for example, the discovery about the microwave background of our universe. That was discovered as a study of noise of satellite communication. And it turns out that noise is actually not noise. It's something really, really important and tells us what happened in the beginning part of our, in the early days of our universe. Okay? So for that purposes, as we study physics, we always trying to understand everything. We look at both the fundamental side and also some small signatures that looks kind of not so fundamental. It's kind of, maybe just noise, but we need, for everything, we will look very closely at them in case we miss some big, big, big discoveries. And another example, actually, I would like to mention was that actually, about this uncertainty nature of the research is, in my field, in condensed matter field, physics. So in the 1970s, 60s, 70s, and one of the main research effort is to find a better superconductor. We know superconductor has no resistance, so electric current can flow there without generating any heat. It will be extremely efficient, for power grid, etc. But one of the biggest problem is superconductor always take place at extremely low temperature. The temperature is so low, practically it's just useless. Okay? So and at that time, the fundamental principles tells us, well, if you want to find a good superconductor, you need to find a good metal. You need to stay away from oxygen. The material should not contain oxygen. And you should stay away from magnets. Okay? It turns out in the 1980s, the accidental discovery of high-temperature superconductors turns out to be exactly the opposite. So you need actually material which is an insulator or very bad metal. You need materials, actually not always, but many of the high-TC material contains a lot of oxygen. And some of them actually has magnetic order, exactly opposite to what fundamental principle told us. And this accidental discovery actually tell us the fundamental things we used to believe to be fundamental actually are not the right fundamental. And the true fundamental actually are discovered in this level of details. And when we study this level of details, sometimes we find the things we believe to be fundamental actually are not right. So in that sense, the fundamental and not so fundamental research are closely integrated together. And there's no clear boundary to split them.
Great, and I'm going to conclude with a comment from my co-host, Professor Roy Clark, which is, surely improving our understanding of the world around us is a huge benefit to society in general. even without the applications. So it's hard to separate these,
Right, yes.
the benefits from just satisfying our curiosity.
Right, yes. So in some sense, this probably is the same coin, just two different sides of the same coin.
Two sides of the same coin, and the human endeavor. All right, well, thank you so much. That was great, and thanks to everybody here and online for the questions, and we'll see you next time.